like what we had in the last one. And again, we don't even need to really do the calculus in this one. We can cheat kind of and just find out which one of these x values is going to result in the smallest slope. So they want us to basically find out, they want us to minimize the slope function. So again, I'll go through how that works. So it's m, we need to know, is always y2 minus y1 over x2 minus x1. So I have here some point, I have an x1, y1. This is 0, 0 because it has to go to the origin. So it's all lines in the xy planes that pass through both the origin. So this is the origin, 0, 0. And let's call this x1, y1. And the point x comma y over here, and let's call this x2, y2. Now I want to find the minimum slope between these 2 points, so I want to minimize m when it's y2, whatever that might be right now, is minus 0 over x2 minus 0, because y1, x1, y1 is 0, 0. Now I have that it's y, because the y value is this over x, and I'm trying to minimize this, but I know something about y. Y lies, this point is always going to lie on this curve. So I want to find out, right, which one of these lines has the smallest slope, right? This is one line. They gave you an example of one line. So this is one of the lines that they gave you. But that's only one, right? You want to find which one of these lines maximizes. You want to find out which one, something like that, right? This is another line, another candidate. You want to find out which one of these lines, right? Which xy, this is a different xy, right? You want to find out which one minimizes slope. And basically what you need to notice is that for all of these points, x comma y, it's always that whatever x is, y is in the form of this, x squared minus 4x plus 9. And now I have a function for my slope in terms of x. Because instead of writing y, I write x squared minus 4x plus 9 over x. And I want to minimize this function. I want to find out what value is going to minimize this function on this interval. Okay? And basically we need to use the extreme value theorem. We need to know that it's going to attain a minimum as long as this function is continuous. It is. This function is continuous from 1 to 4 because it's a rational function, and a rational function is continuous on its domain. And the only value that's not in the domain of this rational function is when x is 0. So what we have here is which I should have went over, is that you could have it that this function attains its minimum at the endpoints. So a function will always attain either its minimum or maximum at one of the other values. So it attains all its extreme values either at the endpoint, right? It looks something like this, right? In which case it attains its minimum on one of the endpoints and its maximum at the other endpoint, or at one of the critical values. So something like this. It could look like this, right? So here, this function attains its minimum when the tangent line is 0, when the slope of the tangent line is 0, which is a critical value. So we need to use that fact here because we don't know. This function on this interval from 1 to 4 could look like the pink graph or it could look like the blue graph. So we want to see which one it is. So in order to do that, I differentiate m prime of x. Let's get started with doing this. The derivative of the top is, so I'm just going to write quotient rule just to be safe, minus g prime times f over g squared. So the derivative of the top is 2x minus 4 times the bottom. minus the derivative of the bottom is 1 times the top. I'm just going to distribute the minus right away over the bottom squared, x squared. And I think this will give me a better idea of what I'm dealing with. So I have x squared minus 4x minus x squared plus 4x minus 9 over x squared. And then this becomes, this cancels with this one cancels with this one. I'm left with x squared minus 9 over x squared. And I want to solve for my critical values. I want to solve for when the derivative equals 0. But we should see that the derivative, the numerator, factors as x minus 3 times x plus 3. And then this over x squared. The parts that are going to make this derivative equal 0 are going to be when x equals 3 and when x equals negative 3. So the critical values is only in this interval that I care about is when x equals 3. So let's draw basic number line. Let's see if it really does attain a minimum at that value. And you want to check to make sure that that minimum is smaller than your endpoint value, because you could have something like this. So I'll show you. So let's say it's 0 here, and then 3, and then 4 right over here. Okay, so here's my line. If I plug in 0, right, to the left of 3, I'm going to get a negative value. So my function is decreasing all here. Then if I plug in 4, I'm going to get a positive value. So my function's increasing. So it is indeed the case that I have it that at 3 I get a minimum, right? It's decreasing and then it's increasing. So this is a min. But now the question becomes, right, you just want to be extra careful and you want to say to yourself, okay, but just because there's a min there, right, it could be maybe something like this, right, which is weird, but, or it could be something like, hold on, let's draw it here. So it could be, right, that I have something like this. Okay, where this value right here would be 3. And then the endpoint value is greater. But really, this point should then give me a slope, and I should be able to eliminate this case. But we want to be extra careful, and you could just test the endpoints. And you could just do that regular algebra and see that 3 will be a minimum for sure. And the answer is C. Okay, or you could even just look, you could graph, no, you can't graph it, but I mean, you could maybe figure out with the calculus, with the algebra, the pre-calculus, what that function looks like. But at the end of the day, yeah, the line with the minimum slope will be at that point, and you don't have to worry about these weird cases because that slope is going to be flattening out. So you don't need to really worry so much about the extreme value theorem and so forth.